Welcome to Advanced Database Management System. In this section, we discuss about database type and various kind of database. What is a database and nature of database? Key characteristics of databases, database security and scalability. Let's enjoy. A database is an organized collection of data, typically stored and accessed electronically from a computer system. It's designed to efficiently manage, store, retrieve, and manipulate data according to various requirements and functionalities. Databases are essential components of modern information systems and are used across various industries and applications, including business, finance, healthcare, education, government, and more. They serve as repositories for structured, semi-structured, and unstructured data, allowing users and applications to store, retrieve, and manipulate data as needed. Key characteristics of databases include structured data. Databases organize data in a structured format, usually using tables, rows, and columns. This structure facilitates efficient storage, retrieval, and manipulation of data. Data integrity. Databases enforce data integrity rules to ensure the accuracy, consistency, and reliability of data. This includes enforcing constraints such as primary keys, foreign keys, and data types. Querying and retrieval. Databases provide query languages, example SQL for relational databases, or APIs, that allow users and applications to retrieve and manipulate data stored in the database. Concurrency control. Databases support concurrent access to data by multiple users or applications while ensuring data consistency and integrity through mechanisms such as transactions and locking. Security. Databases implement security measures to protect data from unauthorized access, ensuring confidentiality, integrity, and availability. This includes user authentication, authorization, and encryption. Scalability. Databases are designed to scale to accommodate growing amounts of data and increasing numbers of users or transactions. Backup and recovery. Databases offer features for data backup and recovery to prevent data loss due to hardware failure, human error, or other unforeseen circumstances. This includes regular backups, point-in-time recovery. There are different types of databases, including relational databases, organize data into tables with predefined schemas and use structured query language, SQL, for querying and manipulation. Examples include PostgreSQL, MySQL, Oracle Database, and Microsoft SQL Server. NoSQL databases, designed for handling large volumes of unstructured or semi-structured data and provide flexible schemas. Examples include MongoDB, Cassandra, Redis, and Apache HBase. NewSQL databases combine elements of traditional relational databases with features for scalability and performance. Examples include Google Spanner and CockroachDB. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about database type and various kind of database. Relational databases are DBMS, NoSQL databases, in-memory databases, time series databases, spatial databases, object-oriented databases. Let's enjoy. Databases come in various types, each tailored to specific data storage and retrieval needs. Here are some common types of databases. Relational databases, RDBMS. Relational databases organize data into tables with rows and columns, and relationships between tables are defined by keys. They use structured query language, SQL, for querying and manipulating data. Examples include PostgreSQL, MySQL, Oracle Database, Microsoft SQL Server, and SQLite. Data analysis and insights. Databases serve as repositories for historical and transactional data, enabling organizations to perform in-depth analysis, generate reports, and extract valuable insights. By leveraging data analytics tools and techniques, businesses can uncover patterns, trends, and correlations that drive strategic decision-making and competitive advantage. Scalability and performance. Databases are designed to scale horizontally or vertically to accommodate growing volumes of data and increasing user demands. Whether it's adding more servers, optimizing query performance, or implementing caching mechanisms, databases provide scalability and performance features to ensure seamless operation and responsiveness. In-memory databases. In-memory databases store data primarily in system memory, RAM, rather than on disk, resulting in faster data access and retrieval. They are ideal for applications requiring high-speed data processing and low-latency access. Examples include Redis, Memcached, SAP HANA. In-memory databases. In-memory databases store data primarily in system memory, RAM, rather than on disk, resulting in faster data access and retrieval. They are ideal for applications requiring high-speed data processing and low-latency access. Examples include Redis, Memcached, SAP HANA. Time series databases. Time series databases are optimized for storing and querying time-stamped data points or measurements. They are commonly used in applications such as IoT, Internet of Things, monitoring systems, and financial analytics. Examples include InfluxDB, Prometheus, Graphite. Spatial databases. Spatial databases specialize in storing and querying geometric, geographic, or spatial data, such as maps, coordinates, and shapes. They provide spatial indexing and spatial querying capabilities for efficient spatial data management. Examples include PostGIS, extension for PostgreSQL, Oracle Spatial, MongoDB with GeoJSON support. Object-oriented databases, OODBMS. Object-oriented databases store data in the form of objects, similar to object-oriented programming languages. They support inheritance, encapsulation, and other object-oriented concepts. Examples include DB4O, ObjectDB. Wide column stores. Wide column stores are designed for storing and querying large volumes of data with high availability and scalability. They organize data into columns rather than rows, allowing for efficient storage and retrieval. Examples include Apache Cassandra, Google Bigtable. Each type of database has its advantages and use cases, and the choice depends on factors such as data structure, volume, performance requirements, scalability needs, and application-specific requirements. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about overview of DBMS, data manipulation, data retrieval, data integrity, concurrency control, transaction management, security, backup and recovery, performance optimization. Let's enjoy. A database management system, DBMS, is software designed to facilitate the creation, organization, retrieval, management, and manipulation of data in a database. It serves as an interface between the database and end users or applications, providing mechanisms for data storage, querying, and administration. Here's an overview of the key components and functions of a DBMS. 1. Data definition. DBMS allows users to define the structure of the database schema, including tables, columns, data types, constraints, and relationships. It provides tools and languages such as SQL for creating, altering, and dropping database objects. 2. Data manipulation. DBMS supports operations for inserting, updating, deleting, and querying data stored in the database. Users can interact with the database through query languages, example SQL, or application programming interfaces, APIs, to perform various data manipulation tasks. 3. Data retrieval. DBMS enables users to retrieve and access data from the database using query languages like SQL. It supports filtering, sorting, and aggregating data to extract meaningful information from large datasets. 4. Data integrity. DBMS enforces data integrity by enforcing constraints, rules, and validations to ensure the accuracy, consistency, and reliability of data stored in the database. It prevents invalid or inconsistent data from being inserted or modified in the database. 5. Concurrency control. DBMS manages concurrent access to the database by multiple users or applications to ensure data consistency and isolation. It employs concurrency control techniques such as locking, timestamping, and multi-version concurrency control (MVCC) to coordinate access and maintain data integrity. 6. Transaction management. DBMS supports transactions, which are sequences of operations treated as a single logical unit of work. It ensures transactions are atomic, consistent, isolated, and durable, ACID, to preserve data integrity and recoverability in the event of failures. 7. Security. DBMS provides mechanisms for securing data and controlling access to the database. It supports authentication, authorization, and access control mechanisms to restrict unauthorized access and protect sensitive information from unauthorized users. 8. Backup and recovery. DBMS facilitates backup and recovery operations to safeguard against data loss and corruption. It allows users to perform database backups, restore operations, and recovery procedures to recover data in case of disasters or system failures. 9. Performance optimization. DBMS optimizes database performance by implementing indexing, query optimization, caching, and storage optimization techniques. It aims to minimize query execution time, reduce resource utilization, and improve overall system efficiency. 10. Administration and monitoring. DBMS provides tools and utilities for database administration, monitoring, and maintenance tasks. It allows administrators to manage database configurations, monitor performance metrics, diagnose issues, and tune system parameters to ensure optimal database operation. Overall, a DBMS serves as a foundational component of modern information systems, providing essential functionality for storing, managing, and accessing data efficiently and securely. It plays a crucial role in enabling organizations to leverage their data assets effectively and make informed business decisions. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about best practices for securing databases, strong authentication, patch management, auditing and logging, data masking and anonymization, database activity monitoring, DAM. Let's enjoy. Securing databases is essential for protecting sensitive data, ensuring data integrity, and maintaining regulatory compliance. Here are some best practices for securing databases. 1. Strong authentication. Implement strong authentication mechanisms, such as multi-factor authentication, MFA, to verify the identities of users accessing the database. Enforce the use of complex passwords and regularly rotate passwords to prevent unauthorized access. 2. Role-based access control, RBAC. Use role-based access control, RBAC, to enforce the principle of least privilege. Assign permissions to roles based on job responsibilities and limit access to sensitive data to only those users who require it for their work. 3. Encryption. Encrypt data at rest and in transit to protect it from unauthorized access and data breaches. Use encryption techniques such as transparent data encryption, TDE, so data at rest and secure sockets layer, transport layer security, SSL, TLS for data in transit. 4. Patch management. Regularly apply security patches and updates to the database management system, DBMS, and underlying operating system to address known vulnerabilities and security issues. Establish a patch management process to ensure timely deployment of patches. 5. Auditing and logging. Enable auditing and logging features in the DBMS to track database activities, including user logins, access attempts, and data modifications. Monitor audit logs regularly for suspicious activity and unauthorized access attempts. 6. Data masking and anonymization. Mask sensitive data in non-production environments to prevent unauthorized access and maintain data privacy. Use data anonymization techniques to replace personally identifiable information, PII, with fictitious or obfuscated data. 7. Database Activity Monitoring, DAM. Implement database activity monitoring, DAM solutions to continuously monitor database traffic and detect anomalies, unauthorized access attempts, and security threats in real time. Set up alerts and notifications for suspicious activity. 8. Regular security audits. Conduct regular security audits and assessments of the database infrastructure to identify security vulnerabilities, misconfigurations, and compliance gaps. Use automated scanning tools and manual techniques to assess security posture comprehensively. 9. Data backup and disaster recovery. Implement data backup and disaster recovery strategies to ensure data availability and business continuity in the event of data loss, corruption, or a security incident. Regularly test backup and recovery procedures to verify their effectiveness. 10. Employee training and awareness. Provide security training and awareness programs to educate database administrators, developers, and other staff members about security best practices, policies, and procedures. Raise awareness about common security threats and social engineering techniques. 11. Vendor and third-party risk management. Assess the security posture of third-party vendors and service providers that have access to the database or handle sensitive data. Establish security requirements and contractual obligations to ensure compliance with security standards. 12. Data retention and disposal. Implement data retention and disposal policies to securely manage the lifecycle of data stored in the database. Regularly review and purge outdated or unnecessary data to minimize the risk of unauthorized access and data breaches. By following these best practices, organizations can strengthen the security of their databases, mitigate the risk of data breaches and compliance violations, and protect sensitive information from unauthorized access and misuse. Additionally, it's important to stay informed about emerging threats and security trends to adapt security measures accordingly and maintain an effective defense posture. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database course. In this section, we discuss about entities, properties or attributes, types of entities, associative entities, granularity. Let's enjoy. Entities, in the context of entity relationship, ER modeling, and databases, represent real-world objects or concepts about which data needs to be stored. They are the building blocks of a database schema and are used to organize and classify data. Each entity typically corresponds to a table in a relational database. Here's a more detailed explanation of entities. Characteristics of entities: real-world objects or concepts. Entities represent tangible or intangible objects, concepts, or events in the real world that are relevant to the domain being modeled. Unique identity. Each entity must have a unique identifier attribute or set of attributes that distinguishes one instance of the entity from another. This identifier is often referred to as the primary key in a database table. Properties or attributes. Entities have properties or attributes that describe their characteristics or qualities. Attributes define the data elements associated with an entity and provide details about the entity's features. Examples of attributes for an employee entity might include employee ID, first name, last name, date of birth, etc. Relationships. Entities can have relationships with other entities, representing associations or interactions between them. Relationships define how entities are connected or linked to each other, and specify the cardinality and participation constraints. Types of entities. Strong entities. Strong entities have their own unique identifiers and can exist independently of other entities. They are represented by standalone tables in a database schema. Examples: employee, customer, product. Weak entities. Weak entities do not have sufficient attributes to uniquely identify them without considering their relationship with another entity. They depend on the existence of a related entity, known as the owner entity. For identification, weak entities are typically represented by tables that have a one-to-many relationship with their owner entities. Examples: order item depends on order, dependent depends on employee. Associative entities. Associative entities, also known as intersection entities or many-to-many entities, represent relationships between two or more entities. They are used to resolve many-to-many relationships into one-to-many relationships. Associative entities are often implemented as separate tables that contain the primary keys of the entities involved in the relationship. Examples: order item, associative entity between order and product. Student course, associative entity between student and course. Design considerations, relevance to domain. Entities should be defined based on their relevance to the domain being modeled and the requirements of the database system. Granularity. Entities should be defined at an appropriate level of granularity, balancing the need for detailed data capture with simplicity and manageability. Normalization. Entities should be normalized to eliminate redundancy and ensure data integrity, following the principles of database normalization. Entities play a fundamental role in ER modeling and database design. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about database management system, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database course. In this section, we discuss about entity relationship, ER modeling, key components of ER modeling, attribute, relationship, cardinality, and multiplicity, steps in ER modeling, create ER diagram. Let's enjoy. Entity relationship ER modeling is a conceptual modeling technique used in software engineering and database design to visually represent the entities, attributes, and relationships between them within a domain of interest. It helps in understanding the structure of the data and the relationships between different entities in a system. ER modeling is typically used during the initial stages of database design to capture requirements and establish a blueprint for the database schema. Key components of ER modeling. Entity. An entity represents a real-world object, concept, or thing that is relevant to the system being modeled. Entities are depicted as rectangles in an ER diagram and are labeled with singular nouns. Example: customer, product, employee. Attribute. Attributes are the properties or characteristics of entities that describe them. Each entity has one or more attributes, which are represented as ovals in an ER diagram and are labeled with descriptive names. Example: customer ID, first name, last name. Relationship. Relationships represent the associations or connections between entities. They describe how entities interact or relate to each other within the system. Relationships are depicted as lines connecting entities in an ER diagram and are labeled with verbs or verb phrases. Example: orders, manages, owns. Cardinality and multiplicity. Cardinality defines the number of instances of one entity that can be associated with the number of instances of another entity through a relationship. It specifies the minimum and maximum number of occurrences allowed in a relationship. Example: 1-to-1, 1-to-1, 1-to-many, 1-to-many, many-to-many. Primary key. A primary key is a unique identifier for each instance of an entity. It uniquely identifies each record within the entity and is used to establish relationships with other entities. In ER diagrams, primary keys are typically underlined or otherwise indicated. Steps in ER modeling. Identify entities. Identify the main entities or objects of interest within the system being modeled. These are typically nouns that represent real-world entities. Define attributes. Determine the properties or attributes of each entity. These describe the characteristics of the entities and are typically represented as fields in a database table. Establish relationships. Identify the relationships between entities. Determine how entities are related to each other and specify the cardinality and multiplicity of each relationship. Refine model. Refine the ER model by adding additional details, such as constraints, business rules, and additional entities or relationships as needed. Create ER diagram. Create an ER diagram to visually represent the entities, attributes, and relationships identified in the model. The diagram provides a clear and concise overview of the data structure and relationships within the system. ER modeling provides a systematic approach to database design, allowing designers to capture the requirements of the system and create a blueprint for the database schema. It helps in ensuring data integrity, reducing redundancy, and establishing clear relationships between entities, ultimately leading to a well-structured and efficient database design. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about database management system, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about relational databases. Key characteristics of relational databases: data integrity, normalization, structured query language, SQL, ACID properties, advantages of relational databases. Let's enjoy. A relational database is a type of database management system, DBMS, that organizes and stores data in a tabular format, with relationships between data represented by shared keys or common attributes. It follows the relational model proposed by Edgar F. Codd in 1970, which defines data in terms of rows, columns, and tables, with each table having a unique name and containing related data. Key characteristics of relational databases: tabular structure. Data in a relational database is organized into tables, with each table consisting of rows, also known as tuples or records, and columns, also known as attributes or fields. Each row represents a single record or data instance, and each column represents a specific data attribute. Relationships. Relational databases support relationships between tables through keys or common attributes. Primary keys uniquely identify each row within a table, while foreign keys establish relationships between tables by referencing the primary key of another table. Data integrity. Relational databases enforce data integrity constraints to maintain the accuracy and consistency of data. This includes primary key constraints to enforce uniqueness, foreign key constraints to ensure referential integrity, and other constraints such as check constraints to enforce data validity. Normalization. Relational databases typically undergo a process called normalization to organize data and eliminate redundancy. Normalization involves breaking down tables into smaller, more manageable components to reduce data duplication and dependency, thereby improving data integrity and database efficiency. Structured Query Language (SQL). Relational databases use a standardized language called Structured Query Language (SQL) for querying, manipulating, and managing data. SQL provides a rich set of commands and operations for creating, modifying, and querying relational databases. ACID properties. Relational databases adhere to the principles of ACID, atomicity, consistency, isolation, durability, to ensure transactional reliability and data integrity. ACID properties guarantee that database transactions are executed reliably and consistently, even in the event of system failures or errors. Advantages of relational databases. Flexibility. Relational databases offer flexibility in data modeling and querying, allowing users to define and manipulate data structures according to their requirements. Scalability. Relational databases can scale to accommodate large volumes of data and support growing user loads through features such as sharding, replication, and clustering. Security. Relational databases provide robust security features such as user authentication, access control, and encryption to protect sensitive data from unauthorized access and breaches. Interoperability. Relational databases support standardized SQL interfaces, making it easier to integrate with various applications, tools, and platforms. Examples of relational database systems: MySQL, PostgreSQL, Oracle Database, Microsoft SQL Server, SQLite, IBM DB2. In summary, relational databases offer a powerful and flexible solution for storing, managing, and querying structured data. They provide a standardized and reliable approach to data management, making them widely used in various applications across industries. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about database, table creation. Let's enjoy. Create table employees. Employee ID in primary key. First name, varchar50. Last name, varchar50. Email, varchar100. Department ID int, hire date. Constraint FK department employees. Foreign key, department ID references department ID. End. Explanation of the above code. Create table employees. This line starts the creation of a new table named employees. Employee ID int primary key. This line defines a column named employee ID of type int integer as the primary key for the table. Primary keys uniquely identify each row in the table. First name, varchar 50. This line defines a column named first name of type varchar, variable length character string, with a maximum length of 50 characters. Last name, varchar 50. This line defines a column named last name of type varchar, with a maximum length of 50 characters. Email, varchar 100. This line defines a column named email of type varchar with a maximum length of 100 characters. Department ID, int. This line defines a column named department ID of type int to store the department ID of the employee. Hire date, date. This line defines a column named hire date of type date to store the date when the employee was hired. Constraint, FK department employees, foreign key department ID references department's department ID. This line defines a foreign key constraint named FK department employees that references the department ID column in the department's table. This ensures referential integrity by ensuring that each department ID in the employees table must exist in the departments table. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about rows, records, tuples. Let's enjoy. Example table structure. Create table myTable. ID int, primary key, name varchar 100, age int. Inserting a single row. Inserting into myTable. ID, name, age, values 1, John 30. Inserting multiple rows at once. Inserting into myTable. ID, name, age,
In this
values
example,
2, Alice
we first
25,
define the structure
3,
of the table
Bob 35,
myTable with
4,
columns
Charlie
ID,
40, name, and age. Then we insert a single row into the table with values 1, John 30. We also insert multiple rows at once using a single insert into statement. Each row is enclosed within parentheses and separated by commas. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about columns, attributes, data types, constraints, indexing, normalization, queries, and retrieval. Let's enjoy. In the context of databases, columns refer to the vertical structures within a table where data is stored. Each column represents a specific attribute or field of the data being stored. Here are some key points about columns in databases. Attributes. Columns represent the different attributes or properties of the entities being modeled in the database. For example, in a database of employees, you might have columns such as employee ID, first name, last name, department, and salary. Data types. Each column has a data type associated with it, which defines the kind of data that can be stored in that column. Common data types include integers, strings, text, dates, floating point numbers, and more complex types like blobs, binary large objects, for storing images or documents. Constraints. Columns can have constraints applied to them, which enforce rules or conditions on the data stored within them. Common constraints include primary keys, foreign keys, unique constraints, and check constraints. Indexing. Columns can be indexed to improve the performance of queries that involve searching or sorting based on the values in those columns. Indexes provide a faster way to retrieve data by creating a sorted list of values for a particular column. Normalization. Columns play a crucial role in the normalization process of database design. Normalization involves organizing the data in a database to minimize redundancy and dependency, typically by breaking larger tables into smaller ones and ensuring each column represents a single piece of information. Queries and retrieval. When querying a database, columns are used to specify which attributes of the data you want to retrieve or manipulate. SQL, structured query language, is commonly used to interact with databases, allowing users to perform operations such as selecting specific columns, filtering data based on column values, and aggregating data across columns. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about primary keys and foreign keys. Let's enjoy. Keys, specifically primary keys and foreign keys, are crucial components in relational database design. They establish relationships between tables and ensure data integrity. Here's an explanation of primary keys and foreign keys. Primary key. A primary key is a column or a set of columns in a table that uniquely identifies each record in the table. It must have a unique value for each row, and it cannot contain null values. Primary keys are defined when creating the table using the primary key constraint. By default, primary keys also typically have an associated index for fast data retrieval. Example, in a table of employees, the employee ID column could be designated as the primary key. Foreign key. A foreign key is a column or a set of columns in one table that establishes a link to a primary key in another table. It represents a relationship between two tables, where the values in the foreign key columns of one table match the values in the primary key columns of another table. Foreign keys enforce referential integrity, ensuring that values in the referencing table's foreign key columns exist in the referenced table's primary key columns. Foreign keys are defined using the foreign key constraint. Example, in a table of orders, a foreign key referencing the customer ID column in the customers table establishes a relationship between orders and customers. Create table employees. Employee ID, int primary key, first name varchar50, last name varchar50, department ID int, foreign key, department ID references departments, department ID. Create table departments, department ID int, primary key, department name varchar50, for. In this example, in the employees table, employee ID is designated as the primary key. The departments table also has a primary key, department ID. The department ID column in the employees table serves as a foreign key that references the department ID column in the departments table, establishing a relationship between the two tables. This ensures that every value in the department ID column of the employees table corresponds to a valid department ID in the departments table. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about structured query language data, querying data modification, schema definition, data manipulation language, DML, data definition language, DDL, data control language, DCL, data transaction control, database administration. Let's enjoy. SQL, or Structured Query Language, is a standard programming language used for managing and manipulating relational databases. SQL is designed to perform various operations on databases, such as querying data, modifying data, defining schema, and managing access controls. Here are some key aspects of SQL. Data querying. SQL provides commands for querying data from a database using select statements. With select, you can specify which columns to retrieve, filter rows based on conditions, sort results, and perform aggregate functions like sum, count, AVG, etc. Data modification. SQL allows you to modify data in a database using commands like insert to add new rows, update to modify existing rows, and delete to remove rows. These commands help maintain and update the data stored in the database. Schema definition. SQL provides commands for defining the structure of a database, including tables, columns, constraints, indexes, and relationships between tables. Commands like create table, alter table, and drop table are used to define and modify the database schema. Data manipulation language, DML. SQL includes commands categorized as data manipulation language, DML, for interacting with data. These commands include select, insert, update, delete, and are used to manipulate data within tables. Data definition language, DDL. SQL also includes commands categorized as data definition language, DDL, for defining and managing database structures. These commands include create, alter, drop, and are used to define or modify database objects such as tables, indexes, and views. Data control language, DCL. SQL includes commands categorized as data control language, DCL, for managing database security and access controls. These commands include grant to grant privileges and revoke to revoke privileges for controlling access to database objects. Data transaction control. SQL provides commands for managing transactions, which are units of work performed within the database. Commands like commit to save changes, rollback to undo changes, and savePoint to set a point to which a transaction can be rolled back are used to control transactions. Database administration. SQL can be used for database administration tasks, such as creating and managing users, configuring database settings, monitoring database performance, and managing backups and restores. SQL is widely used in various database management systems, DBMS, such as MySQL, PostgreSQL, Oracle Database, Microsoft SQL Server, SQLite, and others. It provides a standardized way to interact with relational databases, making it a fundamental skill for database administrators, developers, and data analysts. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about MySQL, features, scalability, performance, security, additions, tools, and utilities. Let's enjoy. MySQL is an open-source relational database management system, RDBMS, developed by Oracle Corporation. It is one of the most popular databases in the world, known for its ease of use, reliability, and scalability. Here's an overview of MySQL. 1. Features. Ease of use. MySQL is known for its simplicity and ease of installation, configuration, and administration, making it ideal for beginners and experienced users alike. Scalability. MySQL is highly scalable and can handle large volumes of data and high traffic loads. It supports clustering, replication, and sharding to distribute workload and ensure performance scalability. Performance. MySQL is optimized for performance, with features such as indexing, caching, and query optimization to improve query execution time and resource utilization. Security. MySQL provides robust security features, including user authentication, access control, encryption, and auditing, to protect data from unauthorized access and breaches. High availability. MySQL offers features such as MySQL replication, MySQL group replication, and MySQL in a DB cluster to ensure high availability and data redundancy, minimizing downtime and ensuring continuous access to data. Community support. MySQL has a large and active community of users, developers, and contributors who collaborate on the development and maintenance of MySQL. Community support is available through forums, mailing lists, and online documentation. Compatibility. MySQL is compatible with various operating systems, including Linux, Windows, macOS, and Unix-based systems. It also supports multiple programming languages and development frameworks. Editions. MySQL is available in several editions, including MySQL Community Edition, Open Source, and MySQL Enterprise Edition, Commercial, each offering different features and support options. The Community Edition is free to use and suitable for small to medium-sized deployments, while the Enterprise Edition provides additional features, support, and services for enterprise-grade deployments. Tools and utilities. MySQL comes with a set of tools and utilities for database administration, development, and monitoring. These include MySQL Workbench, GUI tool, MySQL Shell, command line interface, MySQL Utilities, and MySQL Enterprise Monitor, among others. Platform support. MySQL runs on various operating systems, including Linux, Windows, macOS, and FreeBSD. It is also supported on cloud platforms such as Amazon Web Services, AWS, Google Cloud Platform, GCP, and Microsoft Azure, as well as containerized environments such as Docker and Kubernetes. Licensing. MySQL Community Edition is released under the GNU General Public License, GPL, which allows free use, modification, and distribution of the software. MySQL Enterprise Edition is a commercial product and requires a subscription for access to additional features, support, and services. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson.